Right, everyone. It's 5 past, so I think most of us are already here. So how about we get started? My name is Julian, and I will be running you through this three-part course, which is an introduction to lamps. And uh, this is brought to you by the Archer 2 training. Archer 2 is the UK's national supercomputer funded by UKRI. It's a system made up entirely of Cray supercomputers. And personally, we help run Archer 2 as part of EPCC, the Edinburgh Parallel Computing company. Uh, so the next 3 weeks are going to be they're going to be done as follows. We're going to have this week is going to be a very brief, very basic introduction of how to run an MD code, what different parts of your MD code mean, and things like that. Then next week we'll delve a bit deeper into LAMMPS. I'll talk about how to compile LAMMPS, specifically on Archer, because that's what we're doing this under. I will talk about how to make lamps perform well, or certain tricks and tips for making lamps perform well on HPC facilities. And I will also discuss some things like what if lamps can't do what you want it to? How hard is it to change the lamp source code, sort of look under the hood kind of thing at what lamps looks like in probably more detail than most people need to know, but it's still quite interesting to do. Then the final week, which will be so the slightly more advanced will be next Monday, same time at on the 11th, from 2 till 4:30 UK time. And then the final week on the 18th of May, we will have an exercise class. I've not yet prepared or finalized the problems for that exercise class, but that exercise class should hopefully let you guys do some performance testing of lamps, probably have something to do with crystallization somewhere in there, that sort of simple things. And the other main reason why we'll have that exercise class is if any of you have any questions you want to ask me at any point, if any of you come up with questions you want to ask or have like more specific questions, that'll be a perfect time for you guys to answer it. And I will be here for 2.5 hours answering any and all questions that you throw me as best I can. Obviously, I do not know everything about lamps, and there's going to be a number of things, a large number of things that I don't know the answers to. This does not mean, however, that you must wait until that final exercise class to ask questions. If you realize that you don't understand something when I say it today, please, by all means, post it in the chat. There is either the group chat, everyone, which I'll keep my eye on, and otherwise you can also private message me. If you click on my name and send me a message, it'll come to just me. No one else will see it. If you're worried about people seeing your question or whatever, you're welcome to do that. And whenever it comes to answering questions, I will ask the question so that everyone can hear what I'm answering and then give the answer as best I can. With that, let's very quickly move to all of the course material. Everything that I will talk about today is can be found on the is this sharing? There we go. Can be found on the Archer. Well, first of all, there's a link on the Archer 2 website, so there's a link to this course on the Archer 2 website, and from there it will take you to a link to this Git page, which has all of the course material. It has the overview of what the course is, with exactly what I just said about what the course will look like, course requirements. Presumably you're all here, so you've all met the course requirements. And then on top of that, you've got here day one. If you click on day one, if you click on day one and it works, you will have all of the material for day one, including the slides that I'll be sharing with you guys. I think I just did an internet speed test and my broadband is not as good as it could be at the moment. Not totally unexpected, but that's all right. So you might need to. It's also got the input script that we'll be using. It'll have a submission script that for running these jobs on Archer, and it will also have here at the end of this session, I will set a small exercise for people who are interested in playing around with this between this week and next week. I will give the answer very early on next week, and you can get all of that here. At this point, it's probably worth saying I ran this course about 6 months ago, and if anyone was there 6 months ago, this, you've probably noticed by now, is incredibly similar to what was run there. So you're welcome to stay if you want to. I don't mind, but I thought I'd give you a heads up. You know, I'm happy for you guys to say I like as many people being here as possible. But if you've seen this one before, just wanted to make you aware that, yes, this is pretty much the exact same material. So with that, let's move on to Archer. So hopefully now you'll see a shell, and hopefully you all have an Archer account. You do not need an Archer account to run LAMMPS or to compile LAMMPS or anything like that, but I will be running everything and showing all of my demonstrations on Archer because that is a fixed system, which means that everyone has access to exactly the same resources, exactly the same way. It's set up the same for everyone. So you log into Archer, you should have a completely empty directory. I tend to set up a, so everyone on Archer has two directories. You either have a home directory, well, you all have a home directory in /home/whatever project /your name, and everyone also has access to a personal work directory. I think for this course, the home directory and work directory size are both equal at 10 gigabytes, so I might be wrong. But quite often for bigger projects, the work directory tends to have more space. So usually one of the first things I do is set up a soft link to the work directory and then do all of my simulations there. For this course, you don't need to do that. But maybe, you know, but if you're using Archer a lot, maybe this is something you want to consider. So, by the way, is the keyboard noise too loud when I type, or is that okay? While people answer that, it's fine? Brilliant. Perfect. In that case, so all of this course material, as I said, is available online on the Git page. It's also available in, let's see if I can remember. It's also all available in Work Y14, which is the current job project. The current project in which we'll be doing this tutorial. So Work 14 shared, and there's a directory called LAMMPS Workshop, and today we're doing day 1, so I'll just copy that over to here. If you go into day 1 material, it's everything that's available on the GitLab page. Maybe the slides are a slightly older version, but apart from 1 or 2 pictures, they should be the same, and I'll make sure to swap them back by the end of the day. So hopefully, so if everyone's on Archer, you can just copy that directory day 1 material across to wherever you'll be running it, because I will be at some point swapping back to Shell to show you guys stuff, either to get you guys to run some stuff here, or to just literally show you guys what the LAMMPS input script looks like. So with that, let's go back to the slides. Yeah, no, there's no way to do that. Cool. Let's go back to the slides. So, and start the introduction proper. First of all, well, You are more than welcome to reuse this material. However, this is just to mention that everything that is discussed here is under a license. Please, feel free to reuse it. Feel free to use any of the files that you've been given access to through this course for things. And use it however you want. However, please don't sell this work. This is work that we've done. We're giving it to you guys for free. It makes sense that you guys shouldn't be able to profit from the work that we're doing. Claire asks to mention that if anyone hasn't signed up yet for an Archer account, you can do so today. Unfortunately, you won't be able to get instant access, but you should have access to Archer tomorrow, meaning that from tomorrow onwards, you can try everything I'm going to talk about. Can I share the path of the Archer course? Yep, I'll share it in chat. The Archer path is work/14/shared/LAMMPS workshop. So, going back to this, please don't reuse this material, or please do reuse this material, but don't reuse it for profit. So the basics, what is LAMMPS? LAMMPS stands for Large Scale Atomic Molecular Massively Parallel Simulator. As with all of these acronyms, I never know whether the acronym came first or whether they came up with the incredibly chunky name first. LAMMPS is developed by researchers at the Sandia National Laboratories over in the States, in Florida, from memory. And you can download it from the Sandia website. You can also, there's a Git page for it and things like that. Everything that we will be covering this session and next session, everything comes from the manual. It's reworded, it's made maybe, I mean, in my opinion, a bit more neat, but you could quite literally read through the entire LAMMPS manual and you would get everything I'm going to talk about and probably a lot more. So today's session, we're going to start, like part of the reason that I showed you the path for the Archer files and everything is because I'm going to show you quite how easy it is to run LAMMPS on Archer. Then I will show you how to run LAMMPS locally, perhaps. Yeah, I will show you how to run LAMMPS on a local system on a single processor because Archer does have some quirks to it, but it might be worth showing you guys how it looks on a local system as well. Then we'll talk through how to prepare a simulation. How do you make your simulation box? How do you put your molecules into your simulation box? What are the different ways of doing that? How do you define different particle interactions? How do you set up neighbor lists? Things like that. Take a coffee break at around 3-ish. And after the coffee break, we'll come back and I'll sort of show you how to, once you've set up your simulation box, once you've set up all your particles, how do you then go from that to, okay, let's actually run a molecular dynamics program and talk you guys through the outputs, maybe talk about some advanced options. I will try to answer questions as they come if I notice them. But definitely before the coffee break, I will go through and answer every question that's been asked by that point. And by the end of at the end of the session, I will again go through and answer all of the questions that have been asked that I haven't gotten to yet. So running LAMMPS. Running LAMMPS on Archer is quite simple. If you have copied across the day one materials into your home directory or into your work directory, you can see that there are a number of files and folders. There's the exercise folder, just like there was before. Then there's a file called in.lj. There's a file called lampssub.pbs, and then there's the slides.pdf. Let's look at lampssub. Lampssub is a submission script. It is a way to tell the Archer scheduler the type of job you want to run. So in this case, you want to run a job which has the name LJ run. You want to run on one node. Each node on Archer has 24 cores. You want the job to be run on the short queue. The reason for that is it gets to the front of the queue faster and runs faster. And your job will run, or rather the scheduler should give your job a maximum of 5 minutes in which to. If your job completes in less than 5 minutes, the scheduler will finish it whenever it's done. And for people who are Archer users on their own time or under their own budget, the scheduler will only charge you for the amount that the job has run, rather than the amount that you've asked or told the scheduler that your job would run. This bit here is just saying launch once you submit the job to the scheduler will read all of those things, and eventually it will assign your job to, in this case, a single free node somewhere on Archer. Once that single free node starts, it will read the commands that you've got below here. It will start at the first line and then do all of the commands as if you were running them on shell. So what are the commands? So these two commands are essentially saying, wherever I've submitted this job from, this is where you run the following commands. So i.e. move to where I was when I submitted this script. Then here, module load lamps. This is, on Archer, we use a module system. This means that there are modules that do loads of different things. I'll show you guys in a sec. Module load lamps just tells the node, please load this specific version of lamps, i.e. the version of lamps that was compiled on the 11th of May 2018. Not the newest version, but it shouldn't make a difference for the job that we're doing. And then finally, we get to the actual lamps command. So Ricardo is asking, do we need to register to be able to use the LAMMPS module? The LAMMPS module is a free module. LAMMPS is an open source program, which means that it is free to use. The people at Sandia do not sell LAMMPS directly. I think they sell some services around LAMMPS, but that's only to industry rather than academia. So LAMMPS is always free to use, meaning that if you want to run the LAMMPS module on Archer, the LAMMPS module is free to use as well. Does that answer your question? So you don't need to specifically register to use the LAMMPS module on Archer. Yeah, brilliant. So once you've loaded your module, you're essentially telling the compute node, you're telling it, I'm going to be running this program, so make sure that you have all of the libraries necessary so that I can run this program. And the compute node will do that, and only then are you able to finally run your LAMMPS program. And the way you do that is because of the way the parallel libraries are set up on Archer, instead of NPI run, you need to use AP run. So AP run is very similar to NPI run for all intents and purposes. Then -N24, you're saying, I want to run a job that's going to use 24 cores, 24 processors. I want to use the executable LMP-XE30. That's just the name of the LAMMPS executable on Archer. -in is a flag saying my input is going to be a file called in.lj, and I want everything that's written to go to a file called output.out. Once we've done all of that, we simply qsub. Once we've done all of that, you qsub lamps sub parallel, and then if you qstat, or rather if you qstat -u $user, you get, if you qstat -u user, you get that a job has been submitted. The person who submitted the job, in this case, is me. It is submitted to this queue, which is the short queue. The name of the job is LJ_run. It's asked for one node, 24 cores on that node, and I've asked for 5 minutes. And status is in the queue. I've run the same command again. It's no longer in the queue because it's already run. It's an incredibly quick job because I kind of wanted it to be done quite quickly. Once that's done, you'll notice that in the same directory, when I ls, there are now more files. There are two files called ljrun, one called .o and .e. The .e file is any errors that came up. All of those error messages will be put in the ljrun.e file. So if we look into that, it's empty because the job ran fine. And the associated ljrun.o file will contain everything that was print to screen, or would have been print to screen. Well, no, I tell a lie, actually. It will just say everything that the scheduling node has output. Other than that, the other files we've got are an output.out file, which is where all of everything that I asked the program to print, I've asked it to go into the output.out file, and so you can see what the LAMMPS output looks like. It tells us that, so it tells us a bunch of stuff. It gives us a lot of information, starting with, well, this version of LAMMPS was compiled on the 11th of May 2018. We already kind of know that. And then it gives us information about, so lattice spacing, how the simulation was split up across different processors, how many atoms the simulation had, and loads of things. And then if we go down a bit, we get lines and lines and lines and lines of outputs. By comparison, it is possible to run LAMMPS locally, and I will now do that on my local machine. So there I've got exactly the same, I had exactly the same before I removed that. So there I have exactly the same LAMMPS input file. And I've already precompiled LAMMPS locally. So when I say locally, I mean I'm now going to run this on my laptop rather than running it on Archer to show you A, the difference in speed, but also to show you B, what the different outputs look like when you're running on your own personal computer, your laptop, or something like that, rather than on a HPC facility. Because a lot of the things that happen on the compute node you would usually see, and while you can get that information out quite easily, showing it, I feel, is important just so that you guys know what LAMMPS looks like when it's running and things like that. So in this case, what have I run? I got exactly the same thing. I'm just going in my personal computer to the file where I've got the LAMMPS executable, which in my case is called LMP MPI because it's MPI compatible, and I'm inputting in .lj, and there it runs, and all of those lines that you saw in the output.out file get printed to screen one by one by one by one. This also takes a bit longer because, well, this machine isn't anywhere near as powerful, and also because in this case I am not running it on multiple processors. If I increase the number of processors, it runs a bit faster. This job is not the longest of jobs. From memory, it's only 50,000. So yeah, so it just happily runs, and it outputs whatever information I've asked LAMMPS to output every however often I've asked the LAMMPS to output information. So in this case, every 500 times, every 500 time steps, it is outputting the temperature, the total energy, the potential energy, the kinetic energy, the pressure, the volume, and the density. and there it's finished running. The very last thing that LAMMPS will output is how long the simulation took. And in this case, it took 34 seconds. On my computer, on 4 processors, it took 34 seconds. By contrast, on Archer, this one's Archer, let's hope this one's Archer. On Archer, it took 5 seconds. Yes, that's entirely correct. Because, yeah, Archer is, for multiple reasons, actually. The first reason why it took less time on Archer because Archer is running on 24 processors as opposed to just running on the 4 processors that I gave it. However, you'd think that I was running on 4 processors. You'd think that Archer should be, no, that's about right actually. So 35 instead of 24, so it's running about 6 times faster. That's about right. I'm hiding some stuff in that, but we'll talk about that at some later point. So that's what I'll put. That's what it's like to run LAMMPS, and that's how you run LAMMPS on Archer. And as hopefully you'll see, you've seen, it's really not that difficult. Moving back to the slides. Sorry about the transitions, by the way. Yeah, so LAMMPS on Archer, I've described the modular packages. I've explained that there's a pre-installed version of LAMMPS, and I'll show you next week how you guys can install your own version of LAMMPS, and also I'll explain why you might want to install your own version of LAMMPS. I've also mentioned that on Archer, if you're wanting to run a multiprocessor job of LAMMPS on Archer, you need to have the correct module loaded. It's always submitted for multiprocessor jobs. For jobs that take more than 1 processor, you must submit them on one of the backend nodes, as opposed to on the head node, on the login node. If I were to try to run LAMMPS on the login node, it will tell me that it is not happy. I'm in exactly the same directory, module load, LAMMPS, was it 11? I think there was a minus sign, wasn't there? So, '18. So I've loaded the same module as I did in my input script, and if I try ap run -n for LMP XC30 -in.j on the login node without submitting the job anywhere. If I run that, it tells me it's not happy. And it shouldn't be happy. So I've noticed that there is a question. The question is, can you give a bit of information on the applications of LAMMPS where it can be used and where it can't be used? Yeah, I'm about to get to that. So what can you use for? To be honest, LAMMPS can be used and has been used for simulations in a lot of different things. LAMMPS, people have used LAMMPS to model biological systems. People have used LAMMPS to model crystals. People have used LAMMPS to model surfaces. People have used LAMMPS to model liquids, fluids, crystallization. Can even model things in LAMMPS like how grains fit in silo, how grains flow out of silo, any granular flows, that sort of thing. LAMMPS is incredibly versatile, and the reason for that is that LAMMPS uses a method of simulation called molecular dynamics. And the way that molecular dynamics works is essentially, to start with, you set up a simulation box with a number of particles, and all of the particles have a position that you assign to them at some time, starting time t. And you can also assign or find a way to assign a velocity to all particles. And then you move that picture ahead in time a tiny amount. You say, okay, all of my particles will move will follow their velocity exactly without deviations from their path for this small time delta t. They move to their new position. So they move to their new position, and once they get to this new position, you calculate all of the forces that each particle feels from every other particle, and based on those forces, you find the new velocities that each particle would have in that new position, and you'll find yourself in a case where you've got new updated positions, new updated velocities, which means that you can move those forward by a further delta t, and keep doing this as long as you like. It's the tricks, the arts are really about being careful about which delta t you use. You don't want, provided that your small time step is small enough that there's no particle interactions, or rather that there's no particles hitting one another too much, as long as your delta t is not so large that, say, two particles that would have collided end up missing each other completely because they were moving too fast, you should get quite good physical results. And so LAMMPS is a molecular dynamics package. It does molecular dynamics, i.e. it does this repetition of steps very well and very fast. There's a lot of other molecular dynamics packages, but LAMMPS is, in my opinion, a very good one. So based on this idea, you can do a huge number of things. There's a lot of systems that can use this molecular dynamics, including all of the ones that I've listed before. What LAMMPS does not consider, what LAMMPS considers is a purely Newtonian view of the world. You cannot, or it is possible but difficult, to include and consider quantum mechanical properties. Molecular dynamics is a Newtonian method, and LAMMPS is mainly a Newtonian software. So, you're not going to be able to get interactions with photons. You're probably going to struggle to, you're not going to be able to simulate photons for starters. You're not going to be able to get reaction dynamics, in the sense of you're not going to be able to get bond formations or breaking in general. There are, as I said, there are ways of doing that, but this won't be covered in this course. So now let's talk a bit more about our simple Lennard-Jones code. And the reason that I'm using the simple Lennard-Jones code is because it's just to get you an idea of what LAMMPS looks like without going too deeply into anything, or going too deeply into anything too complicated. So for our program, let's look back at the code that we just ran on Archer. For our program, if we look at in.lj, I've commented this code so that hopefully it'll still make sense, or everyone will be able to make sense of it even when they go away after this. But I've split up the code into different bits. The first part is setting up the simulation box. By this I mean preparing all of the particles that'll be run, that'll be simulated, saying how big they are, saying how big the box is, saying what type of box it is, that sort of thing. The very first command we get is we define units. And in this case, we're defining units as being Lennard-Jones units. What that means is essentially you're saying, so you can, LAMMPS does a number of different units. You can have scientific units. There is definitely a way of doing SI units. You can do metallic units. I've never used those. There's a number of different units that you can use. Here we're using LJ units, and LJ units are also known as reduced units, if any of you have heard of that. And the basic idea of that is you're saying, okay, instead of considering my sizes, my positions, my energies relative to some preset scale, I will scale everything so that all of my lengths, all of my distances are compared to the average size of one of my particles. All of the energies are comparable to the minimum of energy when two particles are really close together, or when two particles come together. The temperature is based on the Boltzmann constants, so everything is reduced. And the reason that you want, or the reason that reduced units are used is because most reduced units will be of order 1. Meaning that whenever you output things, it'll be more or less 1 for any energies of any significance. It'll be more or less 1 for any distance of any significance. And by more or less, I mean it'll be somewhere between 0.1 and 10. The traditional reason why these units were used is because it saved a lot of memory on the original early computers. It saved a lot of memory. Having a bunch, the systems that were originally looked at here were atomic systems. And actually the Lennard-Jones fluid, the one that we are currently simulating in this setup, is one of the very first systems that was simulated using molecular dynamics. And the question was, what if you take an inert molecule, say argon, and you freeze it and freeze it and freeze it? How does argon react? Argon is sort of what is typically the best comparison in real life to what a Lennard-Jones fluid is simulating. It's not drastically exciting, but it's got a lot of easy things for tests of, or it's got a lot of nice properties for when you want to test principles. For instance, it's inert, it doesn't have electrostatic effects, loads of things like that. Argon, however, is incredibly small, meaning that if you wanted to simulate that, well, you would need to, argon is really small, meaning that, it's angstrom in size, so 10 to the minus 10. If you're using SI units, that's a lot of zeros to keep track of. That's why people use reduced units instead. It's to keep everything in a nice, easy to understand scale. The atom style atomic is just saying, well, okay, what do my particles look like? By saying atomic, I'm saying that they're, at least in your dynamics point of view, I'm saying that my atoms, that my particles, the molecules in my box, are all atoms or like atoms. Here I could have said other things, like there's an atom style aspherical, for instance. So if I wanted to simulate rods or platelets or things like that, I could have put that instead. But here in this case, by saying atomic, I'm saying all of my particles are spherical or more or less spherical. Next, we move on to dimensions. And here I'm specifying that the simulation I want to run is a 3D simulation. LAMMPS allows you to do 2-dimensional simulations. I'm not aware of anyone doing 1-dimensional simulations, but I imagine that it's possible if you really want to. But here we're in 3D. And next we define our boundary conditions. And the boundary conditions are essentially saying, what does the edge of my simulation box look like? I've got a simulation box which is in 3 dimensions, so a cube. What happens at those edges? Is there nothing past those edges? Does an atom that gets to that edge, does it go through that edge, or does it bounce off of that edge? Is there a wall? What sort of thing happens? Here I've defined all 3 of my boundaries as being periodic. And now I'll show you really quickly what a periodic boundary condition means. But a periodic boundary condition is looks like this picture to the left. And in this case, our simulation box would be only the central box. And it's got a couple of particles, and those particles are moving. And you'll notice that there's a particle here, this blue particle to the on on the left side of the box, which has an arrow going to the right, that particle could easily have been in the box to the left of it. And likewise, at the bottom of the box, there is a particle that is moving at a velocity such that it would go outside of the box and end up in the box below it. The way periodic boundaries work is we consider that particles wrap. Provided that our box is large enough that we have enough particles in our box, we can simulate good sound physical systems by saying, well, okay, our system is large enough that the interactions we care about, whatever happens in this box, shouldn't be affected by whatever happens in the box next to it. Or rather, whatever happens in the center of this box shouldn't be affected by whatever happens in the center of the box next to it. So that means that, roughly speaking, we could shift the center of the box in space to say that, we could move all of our particles around to say that, instead of the big red particle in the top right corner, we go to the bottom left corner particle and say, well, is there a way of shifting the center of the box so that we're basing it on that particle instead? And what periodic boundary conditions does is essentially it says, well, let's pretend, like, if center to center, center box to center box interactions, if two particles in the center of their box cannot interact, then we should be able to shift our box to somewhere else, and the box at the left corner, bottom left corner, shouldn't interact with the box at the bottom left corner of any of its periodic images. That kind of follows. And once you're in that situation, you can say, well, okay, in that case, why don't I say that if a particle leaves my box through the bottom left corner, it can come up in the top right corner as if it was the particle from the bottom left corner of the top right box that had moved in. Those two particles weren't interacting or weren't interacting much. We should all be fine. That's what periodic boundary conditions are. I hope that makes sense for everyone. And moving back to our input script, then we start to define what our simulation box looks like. So here we're saying that we are going to set all of our particles on a SC means simple cubic in a simple cubic box. The box is going to have a number density of 0.6. So essentially what we're saying is we're telling LAMMPS, I'm going to make a box, and that box is going to have a simple cubic structure, and every point on that simple cubic structure is going to be separated such that the total number density, i.e. the number of particles per volume of the box, is 0.6. Then we define a region. In this case, we're defining a region, which is a box. We're defining a region, and we set a name for that region. That region I have called box because, guess what, it's going to be a box. That region is going to be of type block. So here that means that the region is going to be it's going to be a rectangular prism. There's going to be a x length, a y length, and a z length. In this case, because this is a box, because this is a cube, I have set the x length equal to the y length equal to the z length. So I am saying I am building a box which has which starts at 0 and finishes at 10x, and starts at 0 and finishes at 10y, starts at 0, finishes at 10z, and there is going to be 1 point for every x, y, and in every direction, meaning that I should end with a 10 times 10 times 10, 1,000 point box. The 1,000 point box will be such that the separation, the 1,000 point box will be large enough so that the overall number density of the points is 0.6, i.e. what I've defined here. I then tell LAMMPS, create that box just like I've described it, and then I tell LAMMPS, create atoms, i.e. for every point in the box that I've just described, put one atom. What we end up with is something that looks a bit like the picture to the left. The picture to the left is a cube of 10 by 10 by 10. You'll notice that there's 10 particles that way, 10 particles that way, 10 particles that way. So it's 1,000 particles. They're all evenly spaced. And here I've reduced the volume of the spheres such that the total density is 0.4. In this case, I got a question asking, is that density in Lennard-Jones units too? Yes, the density is in Lennard-Jones unit. So in this case, that would mean that the volume of the box is described in units related to the size of the particles. So that's how you set up your box, and then, I mean, you know, once you've set up your box, it's a case of what do you want your particles to do? How do your particles interact with each other? Because at the moment you can set velocities for all your particles, but if they don't have a way of interacting with one another, they're just going to go and carry on in their velocities as long as they want without anything happening. You don't get any interesting physics out of this. So once you've done that, you need to define your interparticle interactions. Here, because we're using a Lennard-Jones fluid, we're going to use truncated and shifted Lennard-Jones interactions. I'll talk through what that means right now. Sorry, sharing screens takes a sec. Yeah, so in this simulation, we are using truncated and shifted Lennard-Jones interactions. What that means is if we've got two particles, the one to the left and the one to the right, and if they are separated by a distance d, based on what that distance is, our interactions will look like the curve here. The way that this interaction is derived is the equation for this interaction is there is an attractive term which goes as 1 over r to the 6th, and a repulsive term that goes as 1 over r to the 12th. The reason for this is, well, it's based on van der Waals interactions. Essentially, van der Waals interaction goes as 1 over r to the 6th. So it's known that when two particles of a certain size are close to one another, they will tend to try to get closer to one another. However, it's also known that you know, two particles can't overlap. So to add that overlapping effect, essentially, Lennard and Jones came. Lennard and Jones, or two people or one? I can't remember. I'll look this up in the break. But they came up with a fake pseudo-repulsion which goes as 1 over r to the 12th to make sure that the energy cost of bringing two particles really close together is really high. So here we are running with just a Lennard-Jones interaction, and as I said, it is a shifted Lennard-Jones. So what that means is we are saying, instead of simulating this to infinity, instead of considering all particle interactions, because obviously, I mean, as you guys can see, even at a distance of 2.4, there's very, you know, the Lennard-Jones curve is very, very close to 0. But so what we're doing is we're saying, well, let's only consider Lennard-Jones interactions if two particles are within this distance of one another. For this graph, the distance is 2.5. In the code, the distance is 3.5 because that's even closer to 0. And essentially what you're saying is if two particles are within that cutoff distance, calculate what their Lennard-Jones energy is. If they are further out than that distance, don't bother calculating it because it'll be so close to 0 that frankly, we might as well set it as 0. However, doing that can cause a discontinuity in the energy profile, i.e., in this case, if we were to just not consider any particle interactions when they're more than 2.5 sigmas away from one another, 2.5 particle diameters away from one another. You could have the edge case of if a particle is 2.51 sigmas away from another particle and moves to 2.5, it would go from having zero force to suddenly, from zero energy to suddenly having an energy jump. And the way we can get around that is by shifting our Lennard-Jones curve by saying, okay, to make sure that doesn't happen, let's move the curve up a bit so that we are sure that wherever we truncate, wherever we cut off our interactions, it is zero. And the way you do that is by adding whatever that interaction, whatever the interaction energy at that distance is to your entire system. Taking away. So, as I've said, we're using Lennard-Jones cut. So that means that we are truncating our Lennard-Jones interactions. In this input script, it's at 3.5 rather than 2.5. The reason that the graph shows 2.5 is because if you go till 3.5, there's not much interesting happening in the graph, frankly. And below that, we've got a pair modify. So pair style is how you define, is where you define what your particle-particle interactions are. There are loads of them. The slide said, well, I looked it up actually quite recently, and there's 221 different pair styles in LAMMPS. There's a ton of them are different variations on Lennard-Jones, but there's also more realistic pair styles, like electrostatic pair styles. You've got some discrete element method pair styles. You've got so granular pair styles, spring styles, loads of things. And one of the really, really interesting one in LAMMPS is a pair style called hybrid, which lets you merge multiple pair styles into one. Again, here we're keeping it simple with just a Lennard-Jones cut off at 3.5. We then have a pair modify style, modify command, and what that says is that pair style I've just defined, I want to tweak it a tiny bit. In this case, the tweak is I want to shift it so that the energy, so that the entire curve moves up so that at a distance of 3.5, the energy is 0. We get rid of our edge case. Then we define for all of the different types of particles in our box, we can define all of our different pair coefficients and masses. So our pair coefficients are essentially saying, in this case, we've only got one pair coefficient because we've only got one type of atom. We only created one atom type, but we could have created a second atom type if we wanted to have a byte dispersed system or any number of atom types we wanted. I looked this up earlier today, and the developers of LAMMPS claim that you can have up to 2 billion different types of atoms in your simulation. However, they also are very aware that at that large number, you'd run out of memory and wouldn't be able to run anything. But you know, that's their thing. In practice, I've seen people run with up to 30 to 50 pair styles, and then there's a lot of things to come up, like to keep on track of. But it's certainly doable to have a large list of different atoms, or sorry, a large list of different particles. In our case, we've only got one type of particle, and we need to. And here we are saying we've got one. We are saying what our particle interactions are. In this case, we're saying that a particle of type 1, when interacting with a particle of type 1, will act as if it has a Lennard-Jones sigma of 1 and a Lennard-Jones sigma of a Lennard-Jones epsilon of 1. What does that mean? That means looking back at the graph that I was showing you guys, we are saying that the distance at which the energy reaches 0 again is 1.0, and the maximum depth of the well is 1.0. Note that this is for an unshifted system. The system is then shifted after this. So we define our interaction like that. And the other thing that we define, which you guys might have seen, is we set all of the particle masses as 1.0. Again, because we're keeping this our system quite simple. If you were doing a more complex system, you might very well include things like, you could include things like electrostatics. You could have different sized particles, as I said. You could have many different types of particles, each of them with a different mass. If you're doing a more atomistic sort of simulation, you definitely would do lots of those sorts of things. Each different type of particle, so say I'm simulating water, my hydrogens would have a different Lennard-Jones interactions from my oxygens, and they would each also have a partial charge, which I would include, which would mean that I would need electrostatic interactions and things like that. Furthermore, keeping going with the water analogy, there's a number of other particle interactions that we're not even considering here. Things like bonds. My waters are made up of hydrogen, oxygen, hydrogen. There are two bonds. There's a hydrogen-oxygen bond. How do you simulate that bond? How do you keep two particles bound? Well, LAMMPS has 17 different bond commands, which essentially say these two particles are bound. Here's how they act when the bond is stretched or compressed. The one I've usually used in there is harmonic dial, but there's a huge number of other bond styles there. There's angle commands. Hydrogen, water, hydrogen has a set angle, 104 point something from memory. How does that angle move about? Does it jiggle or is it fixed? You can set those parameters to fix your simulation. There's also dihedral commands. If you're starting to get chains of particles, that middle bond has a torsion to it. How hard is it to twist that? For that, you would use one of the dihedral commands if you want to consider those. And then there's also the improper styles, which are more to do with planar twists and things like that. I've honestly never had to use them, though I know a couple of people who have. And yeah, so then the next thing that we'll look at is very quickly talk about neighbor lists before the break. The next bit in our code is the neighbor list. And here we say that we want a neighbor list, which has a cutoff distance of 0.3 and a modify. I'm doing this the wrong way. I should show you guys the slide first. So neighbor lists. What's the idea of neighbor lists? As I said, you can spend a lot of the way that molecular dynamics works is that once you've got all of your interparticle interactions set up, all of your particle-particle interactions, your bond interactions, your angle interactions, whatever you want, you then go through the entire list of all of the atoms you've got, and you say, okay, atom 1, how do you interact with atom 2? What's your energy? What energy do you have from your interactions with atom 2? What about from atom 3? What about from atom 4? Etc., 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 etc. And once you've added all of the different energies, from that you're able to get the forces, from that you're able to get the velocities, which you need to get to the next time step. However, if you have, as in our case, if you have an energy that dies off very quickly, or if you have an energy that is truncated, why waste time calculating the interaction that a particle in the corner of the box has with a particle which is all the way on the other side of the box? Or because we've considered a periodic boundary system, why waste time considering how a particle in a corner of the box would interact with a particle in the center of the box, especially if that distance is much, much greater than the interaction distance. And one of the ways that you can save a lot of time is by considering neighbor lists. And essentially what you do here is you're saying, okay, instead of calculating calculating my distance, the distance between all of the other particles every time step, how about I calculate the distances between all of the particles only every few time steps, and only particles within a neighbor cutoff, which is bigger than my interaction cutoff. Only those particles will I calculate my energy with for the next small number of time steps. That greatly reduces the number of computations and should speed up your simulation. However, in choosing that cutoff, you need to make sure that a particle outside of your interaction range, i.e. outside of your Lennard-Jones cutoff, doesn't come into your Lennard-Jones cutoff without you being made aware of it. So you need a neighbor cutoff which is large enough so that particles can't sneak in without you having calculated them. Or you can set your time step for how often you update your neighbor list to be such that that doesn't happen. Otherwise, you're no longer simulating anything that's physically relevant. And the way we do this in LAMMPS is by adding a neighbor command. And in our case, the neighbor command, we just say we want to make a neighbor list, so we announce neighbor, and we say our neighbor list is 0.3 sigmas, so 0.3 particle diameters bigger than whatever our cutoff is. So in this case, our Lennard-Jones cutoff is 3.5. Lennard-Jones cutoff is 3.5. So we're saying our neighbor list is 3.5 plus 0.3, 3.8. And every so often, we will look at all of the particles within a diameter of 3.8 from every particle, keep a list of those, and for the few steps between when we update the neighbor lists, i.e. between when we make this check again, we only consider interactions with particles in that list. And that can greatly improve the efficiency of the code. But as I mentioned, you need to define how often you update the neighbor list, i.e. how often you check that there's no new particles within this larger cutoff, because otherwise particles might sneak in and you'll get wrong physics. The way you do that in LAMMPS is with a neighbor modify. In your neighbor modify, you state a delay time, and the delay is essentially say you're telling LAMMPS you are not allowed to build a neighbor list unless this many time steps have happened. And you also need to tell it an every time. And the every time tells LAMMPS you must build, or if you can, you must build a neighbor list every this number of time steps after a delay. The delay must be a multiple of the every command. So in this case, every 1 delay 10, that would mean that every 10 time steps, we calculate how many particles fall in the 3.8 diameter of each other, and we only look at interactions for those that have fallen within that cutoff for the ensuing 10 time steps. And after those ensuing 10 time steps, only then do we consider again how many particles are still in that cutoff or how many particles have popped out. You can set that. You can set your delay and your every to higher numbers, bearing in mind that the delay must always be 0 or a multiple of your every. If you set your delay to 0, then you will update every. Yes. So sorry. Someone's asking a question in the chat. 3.8, not 2.8 for the neighbor radius, or am I missing something? Yes, you're absolutely right. I'm getting it wrong. In this case, yes, the neighbor list cutoff should be 3.8 sigmas as opposed to 2.8 sigmas. Sorry about that. So where was I? Yeah, so the delay must be a multiple of the every. So in this case, we've got a delay which is 10 times the every. And essentially, for our simulation, our simulation ran for a total of 50,000 time steps. We had a delay of 10, meaning that we're only building a neighbor list every 10 time steps. And, we must wait 10 time steps before building our neighbor list, and we had an every of 1, which means that as soon as that delay is over, we build the neighbor list. So 50,000 time steps, and one of the information at the bottom of the output from LAMMPS tells you the number of times that the neighbor list was built, which is 5,000 or 4,999. That plus or minus 1 is to do with when it starts counting the first time step. So with that, we're about halfway through. We are about halfway through the practice input script that I wanted to talk you guys through today. So I think that this is probably the perfect time to take a coffee break or a drinks break, or just not have to listen to me for the next bit of time. We'll restart this at 3:30. Well, first of all, I'd like to answer the questions. There were a couple of really interesting questions that were asked during the break. The first question is, if you're using Lennard-Jones units, then do the values of epsilon and sigma always have to be 1 and 1? And the answer to that is no, they do not. And basically, I'll try to demonstrate this as best I can using the slides. But basically, two things. At the moment, we are only simulating a single type of particle. So I set them both as 1 and 1 because that's the easiest number to set them as, honestly. But now let's imagine that we've got a system where we've got 2 different particles, one of which is has a diameter that is twice as large as the other one. Then in that case, the particle diameter of the smaller particle should have a sigma which is half the size, more or less, of the larger particles, because sigma is your particle diameter. So that second particle would have, if our larger particle has a diameter of 1, that second particle would have a sigma value of 0.5. The other thing as well is the epsilon. The epsilon represents the depth of the Lennard-Jones well, i.e., what the lowest point is. Now, too small. That depth, the minimum. The minimum of the Lennard-Jones curve is there to represent van der Waals attraction, i.e. 2 particles of certain sizes that are close to one another will come together through van der Waals attractions. I hope I'm not getting this wrong, but I seem to recall that the strength of van der Waals interactions, i.e. the depth of that well, is linked to the size of your particle. The bigger your particle, the lower that energy well should be physically. So if you wanted to have a physical system like we've got here, where you've got some large particles, some small particles, you would expect that the smaller particle would, by definition, have a lower sigma value because it is of a smaller diameter. And you would expect it also, if this was a physical, like a real-life physical system, to have a lower epsilon value. Hopefully that answers that question. The other question I got was, when would you use an atom style that is different from atomic? And for that, let's actually have a look at the LAMMPS webpage. So let me make that bigger. Let's not make it too big. There we go. Hopefully everyone can read this. But this is directly from the online LAMMPS manual. Directly from the online manual, and it is the page that describes the atom style command. And this is actually a good example of what the LAMMPS manual looks like generally. So I'm glad that this question was asked because I get to show this off, because it is a very nice manual. And it will tell you always at the start, it will tell you syntax. Here's how you use the command. In this case, you write atom style, then you name the style, and if it needs arguments, you name the arguments. It then tells you, here's a list of all the styles you can have, and you've got angle, atomic, body, etc. We'll look at them in a sec. And then it tells you some of the arguments that you can have. And it says, some of the arguments only work when you've got certain styles in play. And there's a bit of examples. And then there's usually a very good description of either the physics or behind whatever they're showing, or in this case, there's a very good description of what the different styles do. I have a list of all of the atom styles that LAMMPS does. We are using the atomic style, and you'll notice that the atomic style only considers what LAMMPS considers default. It is the bare minimum style. It does all of the defaults, nothing more, nothing less. If you want something that's slightly more, interesting, let's say you've got something with charges. This doesn't do charges. You'd need to use a style which I think you'd need to use full, which considers the molecular part as well as any charge. If you're doing something which has, inertia or moments of inertia, things like that, you'd need the body style. If you've got dipole interactions, you'd want the dipole. The dipole style. If you're looking at non-spherical particles, ellipsoid perhaps. I think there's another non-spherical particle. I can't remember where it is. I think here. Or am I making that up? I seem to be making that up. And things like that. This middle column tells you what they're, what they add to the basic package, to the basic atomic package that we're currently using. And then this last column tells you, here's some things you can simulate with. So for instance, at the moment, we're only looking at coarse-grained liquids, which Lennard-Jones fluid is very much a coarse-grained liquid. Could also do coarse-grained solids and metals. But instead, the angles is for, polymers with certain stiffness. The full is often used in biomolecules, aspherical particles for ellipsoids, etc., etc. So there's a lot of different atom styles. We're using the simplest one here because this is a simplest case scenario, but it doesn't have very much shiny additions to it. Hopefully that answers that question. And if so, let's carry on with the lecture. The next thing we're going to look at is, so far we've looked at how do you set up your simulation box, how do you set up your particle-particle interactions, and we've looked at a tiny bit of code to make your simulation run slightly more efficiently. Now we're going to look at how do you tell LAMMPS this is what you need to do. How do you tell LAMMPS, I want you to run this simulation for this amount of time, I want you to output this information, I want you to run with these parameters fixed, etc. This is what this second half of the session is going to be about. To start with, I'm going to quickly move that there. We will start with simulation fixes. A fix in LAMMPS is essentially a command. You're telling LAMMPS, I want this property to be within this certain parameter, to have this value always. So you're setting a general parameter. You're fixing or setting something like a temperature, a pressure. You can set gravity if you want, background flows, whatever you want. In our case, we've only got two fixes at the moment. We've got one fix here, which is I've called it 1 inventively. And it is a fix that I have decided will affect all particles, and it fixes NVT. This is, for those of you who are into thermodynamics, this is the canonical ensemble fix. What I am saying here is I am telling LAMMPS, I want you to run a simulation, and in that simulation, I want you to make sure that these never vary or vary by very little. I want you to fix the number of particles, i.e. if we lose a particle, stop the simulation. I want you to fix the volume of the simulation box, i.e. no fluctuations in sizes because of pressure. The pressure can vary here, but the volume must stay the same. Last, I want you to attempt to control the temperature. I say attempt to control the temperature because actually keeping the temperature exactly fixed is incredibly difficult. And we'll get to why in a bit. But I want you to attempt to fix the temperature. And I want you to attempt to fix the temperature T. I want the temperature at the start of the simulation to be 1.0. I want the temperature at the end of the simulation to be 1.0. And I want I want the program to make sure or help that temperature be at the right place on a rolling average of 5 time steps. So very quickly, I want to show you a bit more on LAMMPS fixes, because, you know, there are a huge number of them. There are 264 fixes on my count, or last time I count, which, right? Yeah. There you go. So there are a huge number of fixes, and they do loads of different things. For instance, you can have a fix to add torque. You can have a fix to enforce 2 dimensions. As I said, we're running a 3-dimensional system, but you can run a 2-dimensional system. If you want to do that, you need a fix. You can have a fix which will evaporate some of your particles away. Obviously, if you do that, or if we try to do that in our current simulation, because we have now fixed the number of particles, i.e. we have said we will keep 1,000 particles from the start to the end of the simulation. If we try to evaporate some of them away, that's taking particles out of the simulation box. That'll crash our system, so LAMMPS wouldn't be happy. You can freeze, you can add gravity, you can set different, so again, very briefly, to control the temperature, there's different ways to try to keep your temperature fixed. And you can set different methods to try to keep your temperature fixed. You can set different fixes. So we're in the NVT ensemble, but you could have NPT, where you fix the pressure and the temperature instead of the volume of the box and the temperature. You can try to fix the pressure and the enthalpy. There's different fixes, so there's an NPT, but there's a different one for if you've got aspherical units, or if you've got spheres, or if you've got different things like that. There are loads of fixes, and we're only going to look at 3 in today's session. So if you're interested, please, this is the, again, the manual is the best place to find this sort of information. Lots of fixes. So as I said, there's 264 fixes. They fix a lot of things. Ours only looks at 2. The first one fixes the temperature and the volume. Fixes the number of particles, volume, and temperature, and tries to set the temperature at 1. And the other one fixes the background flow to 0. The other thing that LAMMPS has is a huge number, a plethora of computes. And honestly, LAMMPS is amazing for computes. There are 138 computes, and again, you can do a huge number of things. You can do a huge number of things with these computes. You can compute things like, I I don't know, let's say you want to compute the center of mass of your simulation box, you can compute that. Let's say you want to compute the center of mass of just a subset of the particles in your simulation box, you can compute that. You want to compute how much a set of particles rotates, you can do that. You can look at radius of gyrations, you can look at kinetic energy for just one part of your system rather than the overall system, and a lot of other things. I'll be showing you guys a couple of computes in a sec, but yes, it's enormous, and all of this stuff is stuff that you would be able to compute yourself in post-processing if you had particle positions and your particle velocities output. You should be able to. These are, all of these are things that you should be able to write your own script for, but LAMMPS has them all already, and it computes these things in a very efficient fashion, which can save you a lot of time down the line. So looking back at our script, we have our first fix, which fixes number of particles, volume, temperature. The second fix fixes the average momentum of your system. If you do not equilibrate your system properly, or if you do something strange with your system, usually if your time steps aren't large enough or aren't defined well enough, then you might get some background flow. Like, let's say, for instance, you randomly assign all of your particles a velocity, and it turns out that overall there's a slight velocity imbalance and most of your particles want to go to the left. Because we're using periodic boundary conditions, what ends up happening is the few particles that want to go more to the left might there's an overall momentum towards the left. Those particles will hit other particles, and slowly that can escalate and escalate and escalate to the point where you have a simulation box where all of your particles are flowing quicker and quicker and quicker in a leftwards direction. With our system, that probably wouldn't have happened, but just to make absolutely sure, I've added this fix, and what this fix says is you take the average velocity, the average momentum of the box, and you reset it to 0. And you reset that momentum to 0, in this case, every 50 time steps. You reset the momentum to 0 every 50 time steps in each of the 3 directions, so the x, y, z direction. Meaning that if you've got some simulation where you actually do want to flow in the x direction, but on the y and the z, you could set the first linear 1 to be a linear 0 instead. So you'd have linear 0, 0, 1, 1 instead of 1, 1, 1. In this case, I want everything to be definitely stable. And the last part is saying, oh, and I also want the angular momentum to be fixed at 0. So I do not want any weird momentum issues. I want my system to look fixed, and that way the motion that I see is the motion relative to a completely fixed 0 velocity box. One thing I forgot to mention about the NVT command is, as part of this command, this is also the command that will state how the simulation will be moving forward in time. And the way that LAMMPS works, at least under the NVT command, at least under NVT and under NPT, is it uses a method called velocity verlet. And the way that this method works is you start your system with known velocities and known forces. From those known velocities and forces, you update your particle positions. From those new positions, you update your energies and your forces, and from those new forces, you update the velocity. It's exactly what I said before, just shown again here with equations. The way that LAMMPS looks at these equations is it considers first, these equations that I've written are the equations that I've written here are the sorry. These equations that I've written are essentially saying, well, okay, let's imagine that you've got your positions and let's say that you've got your velocities and your forces and your positions at time t. How do you then find at time t plus delta t your new positions? And the way you do that is simply you take a Fourier transform of that, and you're able to get your new velocities and positions at time delta t from your old positions, your old velocities, and your old force, multiplied by how big that time step is. And then from that, you can move forward to find your new forces, which is based entirely on your new positions. And then from that, you can move forward to find your new velocities, which is based on your old velocities and the change in force between the old time step and the new time step. This is the non-velocity. This is the normal Verlet algorithm. The way that LAMMPS does this is by using a velocity Verlet algorithm, which is exactly the same as here, except instead of considering everything from a position point of view, you first consider you try to solve all of these equations from a purely velocity point of view. The reason why LAMMPS does that is because they have found that this method gives more stable simulations. We are trying to simulate physical systems here, and while in physics energy is always conserved, in simulations, because you are discretizing a continuous process, because you are splitting everything into small time steps or small snapshots, instead of having everything flow like it would naturally, there is some losses, or there are some losses rather. The developers of LAMMPS feel that the velocity Verlet method leads to smaller losses in energy, i.e. a more stable system, than the normal Verlet algorithm. Note that in this case, by the way, all of the equations, all of the right-hand sides of the equations are simply expansions of the left-hand sides of the equations. But so part of the NVT fix, as programmed in LAMMPS, will tell the program, by the way, you're using velocity Verlet. So moving back swiftly to our code, after our fixes, we have our final setup. And in our final setup, the first step of this is I'm telling LAMMPS, okay, at the start of our simulation, I want all particles, I want to set particle velocity. I want all of my particles to get a velocity, and I want my particles to, I want all my particles to have a random velocity. I want the average particle velocity to be such that the temperature is 1. Here is a random seed, and I want no overall momentum to my box. LAMMPS will then take, generate a bell curve, assign different particles different velocities randomly from that bell curve based on this random seed. And then once all the particles have their velocities, it'll move to the next step. The next step is saying, here's the time step I want to run at, in this case 0.05. The reason I chose this step is because it helps the simulation run, or rather at this step the simulation will run. If you set your time step too large, you will miss out important physics. If I set my time step to something enormous, in this case like 1, then it is entirely possible for two particles that are next to one another to move so quickly past one another in that time step that, whereas in real life they would have collided, they end up with the left-hand particle on the right-hand side and the right-hand particle on the left-hand side, having never touched or seen each other. Likewise, if you take too low a time step, you will end up with a super slow simulation where slowly, slowly, slowly those two particles will come together and your simulation will stop before they've even hit. Finding the correct time step is a bit of a dark art. One of the ways that you're probably best off doing that is to look at things like the diffusion of your particle, average diffusion of your particles, and base it on that. The next thing we have is the thermostyle. And as you saw in the when I first ran the simulation at the start of the session, when I ran it on my local system, there were a number of columns that were being output. And those columns were, there they are. Those columns were like so. The first one was time step, then I said there was temperature, total energy, potential energy, kinetic energy, pressure, volume, and density. The way that LAMMPS knew to output these properties and no more, no less, is because I set in the script, I set the outputs that I wanted. I set a thermostyle, and thermostyle essentially is a flag for LAMMPS. Please output the following. I want to output a custom selection of information. LAMMPS has some preset thermostyles, but in this case, I want what I choose rather than what LAMMPS has as prepared. And the things I want to output are the simulation time step, the temperature of the system at that time, the total energy, the pressure, the potential energy, i.e. all energies caused by interparticle interactions, the kinetic energy, the pressure, the volume, and the density. And then I want that to be output every 500 time steps. So those two comments, you're just saying these are the overall average properties that I want LAMMPS to output. And finally, run style let, that is to enforce, rather than LAMMPS using the velocity verlet that it would otherwise, I am enforcing that LAMMPS uses the verlet algorithm. Rather than the one before. And finally, we get to the run command, and the run command tells LAMMPS, please run this for 50,000 steps. At this point, let's have a look at what's then output, because we've seen it before, but what does the output look like? Well, firstly, LAMMPS will output everything to a log file. So regardless of whether or not you name it, you can name your log file, but if you do not, LAMMPS will always output to this file, log.lamps, which I'm currently highlighting just to show which file it is. So this file, log.lamps. Furthermore, it will automatically output everything to screen. In this case, I made sure that everything that is output to screen went into output.out instead. If we look at the head of both, they look different. The reason for that is that the log file will output every single line that was in our LAMMPS input script. And then whenever it needs to do something, it will output the result of doing something. So LAMMPS reads all of the text that I've commented at the start, then gets to unit LJ. Okay, it takes the unit LJ box, gets to atom styles, it takes that atom style box, dimensions, it takes that, boundaries, it takes that, etc., until it gets to lattice. And lattice is the first one where LAMMPS needs to set something. And it sets the lattice and says, well, okay, if you want a lattice, if you want a square cubic lattice, simple cubic lattice at a density of 0.6, that means that your x, y, and z lengths need to be 1.18. The way you get that is you would take the cube root of 1 over 0.6. Then you're setting your region, you're creating your box, and once the box is set, then LAMMPS will create the box using so you're setting a box which has 10 10 points on it per dimension, and LAMMPS will then multiply those 10 points by the 1.18 in the lattice spacing to give you a final box, which is 11.8 by 11.8 by 11.8. It then says, I'm going to split this across the number of processors you have, creates the box, etc., etc. So you get a lot of information from the log file. You do not get just straight to screen. In fact, when things that go straight, whenever anything crashes for whatever reasons, usually the log file is the best place to look at. LAMMPS will output everything into log.lamps unless or until you name a file like so. If you put a log command and then say name that file, everything above this line, i.e. everything above the line log.test, log.test, will go into the log.lamps file. Everything below that line, everything that happens below that line, so in this case, that includes the full simulation run because the run is below that line. Everything that LAMMPS does after that will go to log.test. And that will be the case until I either rename a log file or stop this one. Another thing I mentioned, and actually this is a great way of looking at log files. Here I have named this fix 1, and below there is a commented fix also 1. Fixes for LAMMPS must all have different numbers. So in this case, if I were to uncomment this code should crash. And I'll just run that to show that it should crash. Actually, let's. But yeah, so this code should eventually crash. What you're seeing at the moment is simply an updated every 2 seconds of the program. And now you can see the program's gone from queuing to running, and now it is in status E for exiting, and now it's exited, the program is running. And if you look, if we look at log.lamps now, at the end, as predicted, I've got 2 fixes with the name 1, and here it says you're replacing a fix, i.e. there is already a fix called 1, but you're saying there's a new fix called 1, and they're not the same type of fix. I don't know what to do. I'm crashing, I'm exiting. That's the line I want to. So make sure to name your fixes different things. The other thing I wanted to briefly talk about is computes, because I've mentioned them, but I've not actually shown you any of them. But basically, up to this point, we've seen everything that was run in that initial simulation we used in LAMMPS, or we ran in LAMMPS at the start of this session. We've talked about, we've discussed step by step. If you have any questions about that, please feel free to ask them now. I'll answer them as we go. But now we'll go on to a couple of other cool tricks and cool things that you can use LAMMPS for by looking at the computes, which, as I mentioned before, is really where LAMMPS shines. And I put them down as advanced inputs. The first one we'll look at is the brilliantly named dub command. I mentioned that most of the things that computes can be used for, you could just get all of that, and provided that you output the simulation on a per atom basis, you would be able to get all of those. You would be able to calculate yourself those properties. However, to do that, you must output all of that per atom information, and the way you do that is through the dub command. What that does is you are setting up a command, in this case, a dump command called to, which will output for all particles a custom set of things that I define myself. You will output every 1,000 time steps. Actually, let's reduce that to 500. You will output to a file called positions.lamps trajectory, or lamps trj. There's a reason why I've called it this, and I'll show you in a sec. And I would like you to, for every particle, every 500 time steps, output the particle ID, i.e., is it particle number 1 in the system, or is it particle number 1,000, or anything in between? The x position of that particle, the y position of that particle, the position of that particle, as well as their x, y, and z velocities. I'm also adding this dump modify command, which is there to ensure that regardless of position, or regardless of which processor finishes first, or whatever, when you output at time step 0, I want the particles to be in exactly the same order as when you output at time step 500, etc., etc. Note that as it stands, this command is after the run command. That means that for our simulation, it would, as it stands, our simulation would run the 50,000 steps and only then consider this dump command, meaning that a dump file would be created with only the particle positions at time step 50,000, but nothing after that, unless there is a dump command below it. Unless there is a run command below it. There is a run command below it, but it is currently commented, so instead what I will do is I will move this up. Make exactly the same mistake a second time. And the code. There we go, it's running. And it's exiting. A bit longer, which makes me think it probably ran. And there you see we now have a folder called positions.lamps trajectory. And if we look into that file, we can see that, as I mentioned, we've got a certain number of lines before we get to the positions of every particles. So let's talk very briefly about what's in this file, because it's actually quite interesting. The first line tells you what is output below it. So here it says item time step. That tells you below me is which time step we're on. So we're starting on time step 0. Fine. It outputs the position at the very start of the simulation. Next item, number of atoms. This simulation has 1,000 atoms. We knew that already. Next item is the box boundaries. Our box goes from 0 to 11.8 sigmas in the x direction, y direction, z direction, and the x, y, and z boundary conditions are periodic. So box bound PP means box boundaries, they're periodic in all 3 directions, and then you get the three dimensions minimum value and maximum value. Next item is for each atom, we are outputting the ID, the x, the y, the z position, and the velocity in the x and y and z position. So the very first atom is on position 0, 0, 0 and has a random velocity, randomly set by our velocity command, of 0.2 in the x direction, minus 1.0 in the y direction, and 0.4 in the z direction. And then it'll list exactly the same thing for all of the particles until we get to, I missed it. There we go. The 1,000th particle, where following that, we get a new item. In this case, telling us that, well, I've run for 500 time steps. You've asked me to output this every 500 time steps. Here's the 500 time steps outputs. And again, all of our particles are in the same order because we had our dump modify. This is all nice and good, but actually, and this gives us a lot of easy things, easy things that we can look at. We can track how far particles have moved over time. We can do a whole number of things. One of the really cool things that we can do, though, is with this, we can visualize the results. And one of the programs that I often use to visualize is a program called Visual Molecular Dynamics, or VMD. And this is installed on Archer as a module, which means that you can load VMD, and then you can run VMD. VMD is happy to input, it's a general purpose visualization program. And it's happy to take inputs from a plethora of different programs. Definitely it works with GROMACS outputs. For people who are aware of GROMACS, it's a very, very quick, very specifically biomolecular software. It works with Amber, it works with a certain, a whole number of different programs, including LAMMPS. And now we get to why did I put my file type as LAMMPS trajectory? Well, that's because VMD will naturally, if you input a positions.lamps trajectory, it will naturally know exactly what setting is being used and immediately output the visuals. Unfortunately, because of the way I'm sharing my screen, I don't think you'll see the full effect, but please feel free to try it from Archer wherever you are. Where was I? VMD positions. Gives you a lot of information about, hi, I'm launching VMD. I'm still launching VMD. VMD is just about launched. Still loading, still loading. If this takes much longer, I'll do it from my place. You're happy, are you happy? You're not happy, yeah. There we go. Sorry about that. So when you first launch VMD, you will get a certain number of windows. The first window you will get is something that looks like this, which is quite literally the GUI for VMD. The next thing, the other window that you'll get is a window that has this lovely, terrible, terrifying, awful mess. And that is, that's our simulation. I'm going to move this back in time, back to time 0. Where you can see, oh, look at that, it's our perfect sphere as it was at the start of simulation. This is not rendering very well. I'm going to do exactly the same thing as I'm showing you here, but from my laptop instead, because I'm not liking this at all. Sorry about that. There we go. So I've just rerun the thing on my laptop and forgot to output the positions because, If anyone's got any questions, this is a great time to ask them because I'll have about 30 seconds to answer them. Probably more than that. Yeah, so it's running, and while it's running, actually, I'd like to take this time to mention, now that we've talked about the fixes, one of the things we'd fixed was we fixed number of particles, volume, and temperature. We are outputting both volume and density. So volume is, volume is just length cubed. And density, if your box isn't changing, density should always stay the same. So the last two columns should be volume and density. And as you can see, these remain fixed throughout. That makes sense because we've told LAMMPS, please keep these fixed. However, another thing that we fixed is the temperature. And the temperature is the second column. And you'll very much quickly notice that we set the temperature as 1, but there are fluctuations in temperature. The reason for these fluctuations in temperature is It's to do, again, with the discretization of the continuous physical flow that we are simulating here. So because there are start-stop motions, a particle will not move up an energy move along an energy path in the same way as it would naturally. It will move, in time step 1, it might be at very close to zero energy, and then in time step 2, it might be at a slightly different energy, but still that is a sudden increase in energy for it, or a sudden decrease in energy for it, that the system hasn't considered well. We are calculating the next position based only on the current forces and the current velocities. And therefore, we end up getting some fluctuations in velocity, we end up getting some fluctuations in energy. So energy is not exactly conserved, but it's almost conserved. This can be exemplified by looking at, if you look, column 3 is the total energy, and the total energy is not staying steady. It's staying close to steady, but it's not staying steady. And the total energy in this case is made up entirely of the particle potential energy, the interparticle interactions that I was talking about, or arising from the interparticle interactions that I was talking about, or the kinetic energies. And if you look at both the potential energy and the kinetic energy, those also are not staying steady. The potential energies are not staying steady because of the effect I just said of we are taking snapshots in a continuous time. But to get the next snapshot, we are assuming that conditions stay as they are now, roughly speaking. So that causes that discrepancy in the energy conservation. So the energy at the next time step will be slightly different from the potential energy at this time step. But from our potential energy, we will then calculate the forces on the particle, and from those forces, we will calculate the new velocities of those particles. So if our energies are not staying constant, then our forces are not staying constant. And if our forces are not staying constant, our velocities are not staying constant, or are not staying at the same average. And that means that if our velocities fluctuate, our temperature fluctuates, because our temperature is linked directly to the average velocity of the system. So naturally, in a molecular dynamics simulation, your temperature will fluctuate. And what we do with the thermostat, what we do when we try to fix the temperature, we're essentially trying to tell the system, okay, we understand that you will naturally fluctuate, but we want to control that as much as possible. And the way we control that is by saying we want our temperature to be 1, more or less. And the more or less means we are okay with the temperature increasing a bit or decreasing a bit, but overall to be 1. And the final number that we'd set in our input script, that was a 5. The simulation's run, so I might as well show you guys. The final number that we'd set in the fix, the 5, that number tells you what size of fluctuations you're happy with. So the lower that number is, the more you want your average temperature to be at 1. The higher that number is, the more you're happy to let your temperature go wildly off course before having to come back to average 1. This is, roughly speaking, a running average of the temperature, but it's based on the unit type you're using. So in this case, it would consider it will try to keep the temperature roughly at 1 over a time not linked to the time steps, but rather linked to it's not linked to the steps. Like if you average any 5 points, they don't necessarily lead to 1, but rather it's linked to what if our time step was 1. And so that's where the fluctuations in energy come in. I will admit, and to be fully frank, choosing what good number to put, what good number to average your temperatures over, choosing that 5th number is a bit of a black art. Usually the way I do that is I run my simulation with a bunch of different numbers for this value, and I would run it with a bunch of different values there, and I would try to minimize the amount of error around energy. But basically, if you put this number too low, you are essentially having to reset the temperature of your system, the velocity of every particle, every single time step. The way that the temperature is sorted is you essentially flick your particles, or a random number of your particles, with a small energy kick to increase their velocity a bit, so that they'll go faster when the temperature is too low, which will ultimately increase the temperature, or you drain some of that energy away, you lower the velocity of some of your particles, so that the overall system will go more slowly overall, which will reduce the temperature when the temperature is too high. If you do that too often, then you are essentially just resetting the temperature every time step, and you're not letting your system flow as it would naturally. But likewise, if you do that too not often enough, you end up in a case where those small fluctuations that we talked about will add up and add up and add up. You can easily end up with, if we were using SI units, you can easily end up with a system that was running happily at 293 Kelvin or Celsius, with 20 Celsius, dropping to 10 degrees Celsius, where the conditions are different. So that was a nice aside. Let's go back to visualizing. We now have that. I've got VMD. That's good. So I showed you guys the control panel for VMD. Now I'll just show you the pictures while I play around with the control panel. You should be able to do that on Archer. It's just a bit of a costly program, so it's a bit jittery. I wasn't too happy with how long it was taking, so that I ended up spending 10 minutes talking about something else. Well, anyways, what I'm doing now is I'm going under graphics, representations, and I am going, that brings out a new pop-up bar. And in the new pop-up, I'm going in drawing method, choosing VMD, and that puts my particles as if they had a radius of 1. However, they've got a radius of 0.5 because they have a diameter of 1. So I'm going to decrease these. This is what my simulation looks like at the very start. And you'll notice it looks very similar to the cube that I showed you guys when I was showing you how the simulation is set up. It's quite densely packed, so I'm actually going to lower this a bit more so that you guys can see further into the box. And then I'm going to start the simulation. And there you go. This is showing you every 500 time steps the new positions of the particles. And it loops around. So there we go. It loops around, it loops around, it loops around. VMD lets you do a whole number of things, including I can pause at any point. I can drag it back to any part of the simulation. I can even go step by step forward if I want. I can turn my simulation. I can rotate my simulation. It's a great visualizing tool. I realize that, you know, it's sort of a bad showmanship on my part to show you a not very exciting simulation of a Lennard-Jones fluid when trying to sell you this tool, but VMD is fantastic. And indeed, if we go back to the slides, VMD, I mean, some people create, frankly, some people create art with VMD. These are just two things that I've taken from the page. But yeah, so you're able to, if you set your settings right, you can have, the top picture, I think, is a protein, but shown as a ribbon-like structure with different colors based on whether, I seem to recall they're hydrophobic or hydrophilic, but don't quote me on that, I don't really remember. And then the bottom part is showing some structures binding to a carbon nanotube. Those look lovely. And by VMD standards, frankly, there's still many better things out there. There's other programs available. I use VMD. Frankly, I mainly use VMD because it's the first one I've used, but there's other things out there as well. One of them is a tool called Ovito, which lets you see multiple windows at the same time. I know that a lot of my friends in dense granular fluids, in the field of dense granular fluids, though I mean, it would be amusing if they were actually in dense granular fluids, but yeah, in the field of dense granular fluids, often use Ovito because that gives them more information that they're after. Then I've also added here a couple of links to some Python packages which can help you with pre-processing LAMMPS or post-processing for LAMMPS. So by pre-processing, I mean what if you want to, what if you need to set up your simulation? These will help you get your simulation ready to run, as in like set your particle positions, set your velocities, things like that. They can also help with post-processing. So if you're trying to get some specific information out of your simulations, you can run those to help get that information out, to extract that information. I've not used either of them drastically much. Of those, I would recommend PizzaPy most because that's the one, sorry, Pizza.py, because that one is developed by the folk at Sandia, and they're the same people who develop LAMMPS. So, it's the most similar to LAMMPS. But I've heard great things about the other two, so thought I'd mention them here. Just to finish off, I wanted to quickly talk about advanced inputs methods and computes as well. Before I do that, I noticed that there was a question. Question. One moment. So the question is, can you tell where we specify force fields in the input file? So yeah, sure, I'm happy to do that. It's quite an easy one. So the way LAMMPS works is you do not specify a force field per se. You instead write out the force field. So instead of saying I'm using this type of force field, you quite often will just write out, so in this case, instead of saying I'm using an amber force field or amber 14 force field or whatever, instead I would write out for all of my particles, here's my coefficient, here's my Lennard-Jones, epsilon and sigma. If they had bonds, I would also write out here's my bond coefficients. If they had angles, I would also write out my angle coefficients. There's ways of speeding this up. Two ways of speeding this up. One of them is using a program called PackMol. And PackMol is a handy little program that'll help prepare, randomly pack your particles ready to use as a data file for LAMMPS. But then you'll still need to include all of your force fields into that. Another thing to do is once you've packed your system with PackMol, you can open it up in VMD, and VMD has a handy tool called Topo Tools with which you can set up your simulation and include all of your force fields in a data file for LAMMPS. A data file is essentially just an input file with all your particle positions, all your starting particle velocities. In there, you can also include all of the masses, all of the pair coefficients, basically all of this stuff that's highlighted can go in the data file in some way or other. If you're interested in data files, this is something that I'll definitely have as one of the exercises, or one of the exercise and examples for the final session. will definitely involve a data file. So if you're interested in those and how those work, I will happily talk about them more then. But basically, the idea is you can replace most of this information with read data and then the name of your data file, and run it that way. So the last things I wanted to talk about, and sorry about this, I'm going to be overrunning a bit. I hope that's okay with everyone. But yeah, so the last thing I wanted to talk about really is computes, and here I've got 3 computes set up. The first one is computing a radial distribution function, and what that tells you is you have a particle at position 0. What is the probability that you will find another particle at a position r, which is greater than 0? So what is the probability that you'll find a particle at position r versus the probability of particles being entirely evenly distributed? And here I've got my compute command, and I've said that I want my RDF. I want my RDF to be computed up to and only up to 3.5 sigmas. And I want that distance of 3.5 to be split into 150 different bins. So every 3.5 divided by 150 will count my particles. And if a particle is in the first, or if a particle is between the first bin and the second bin, it is in the cutoff for the second bin, so it would be counted for the second bin. If a particle is in between the second and third bin, it will be counted for the third bin, etc., etc. The next line of code is, so LAMMPS will compute this, will find whatever that is for every particle at every time step, or averaged over every time particles for every time step. However, that's not drastically interesting to us. What we care about is the average over the entire simulation, or at least the average over part of the simulation. So here what I've done is I've used a fix to average all of those outputs. And essentially I'm telling my average, I'm telling LAMMPS that I want this to be averaged. I want LAMMPS to take a reading every 25 time steps for the last 100 time steps. For the last 100 times where this is applicable, and my simulation, and this is going to be for a simulation which runs 5,000 steps. So here, what LAMMPS will do, you'll notice there is a run 5,000 command right at the bottom here that I've highlighted real quick. I'm telling LAMMPS this next bit's going to take 5,000 steps, and for the last 2,500 of those, every 25 time steps, take an RDF, and then at the end, average those 25. The next thing I'm looking at is the mean squared displacement. The mean squared displacement is the average distance that particles move over time. So how far does a particle drift, and how quickly does a particle drift outside of its cage of particles? And the last and like before, I don't need to specify bins or anything. It's just going to give me the straight output. Here's the average at time step 1. Here's the average at time step 2. And it'll just happily do that. Here I need another fix, but the reason I need this fix is that LAMMPS will naturally give me the mean squared displacement, but per particle. So whereas the RDF, whereas the radial distribution function is averaged over all particles, and I'm using a fix to average that over time, here, for the mean squared displacement, I get an answer over time, which varies over time, which I want to see how that varies over time, but I get one answer for every particle. So in this case, what I'm trying to do is to get all of that data and average it over all of the particles. So that's what this fix is doing there. And the last fix is the velocity autocorrelation function, and that is trying to tell you how quickly a particle forgets the direction in which it is going. So I've calculated all 3 of those, and I did the run while I was talking to you guys about the VMP. So that's already been done, and you'll notice that now there's a couple of outputs, including mean squared displacement, radial distribution function, and velocity autocorrelation function. And if we want to look at them, I'm using GNU plot because everyone loves GNU plot, or I do anyways. I'm going to start with the radial distribution function. There we go. We get our radial distribution function. Well, you guys can't see it. Sorry, this is terrible on my part. Pause. There we go. We have a radial distribution function, and what this is showing us is that between a distance of 0 sigma and 1 sigma, you expect hardly any particles, which is understandable. We've already said that the particle diameter is 1 sigma, which means that two particles can't get closer or shouldn't be able to get much closer than 1 sigma's distance apart. You'll notice that there's some overlap. That's because sometimes some very fast atoms will be able to smash through, or have some small limited overlap before they're repulsed. But overall, you get hardly anything below 1. Then what do you get? Well, you start to get a peak. This peak represents the first shell of particles. So roughly speaking, when you have one particle around it, you'll get a certain number of particles that will naturally fall around it in the first shell, and then you'll get a second shell of particles around it, and then etc., etc. But those are very random. Eventually, this averages out to 1, because if the system were evenly distributed, then overall you'd expect that there is one atom everywhere. And indeed, if this was a completely even system, it would just be a line at 1. The next thing that we're going to look at is the velocity autocorrelation function. The mean square displacement, sorry. Let's get rid of it. I'll explain why that bar showed up in a sec. But here is your velocity autocorrelation function. And essentially that's telling you the bottom axis is time steps. We had a scale where every time step was 0.05 reduced time. So, this should be times 0.05, which I can easily do. There we go. So the bottom axis is time, and the y-axis is distance. This is showing you how far, on average, a particle has drifted from its starting position over the simulation. And on average, this is telling you that your particles have diffused a grand total of 200 sigmas, which is way, way, way bigger than our simulation box. And the only way that we were able to do that is by using periodic boundary conditions, meaning that a particle, whenever it left through the left-hand side of the box, one of its images would enter through the right-hand side of the box. That's the only way we can get these sorts of distances. More interesting, though, is if we zoom in to just this part, there's a couple of interesting things. The first one is you'll notice that this starts off as being quadratic. That's normal. Going back to the, not particle cage, but particle nearly cages that we were talking about before, at the start, a particle all of the particles will have been restricted in their movement by their neighbors. But as they're able to break out of those restrictions, on average, the distances start to increase and increase and increase. And we move from this quadratic start into this linear region. The slope of this linear region, by the way, is directly correlated to the velocity, to the diffusion constant for this system. So if you remember earlier in the talk, I mentioned that you wanted a time step such that you were, that was heavily linked to diffusion. Basically, you want a time step that will show you both this quadratic behavior and then this linear behavior. That's what you're looking for. So in this case, it looks like we've achieved it. Admittedly, I'm the one who set up this code, and it did what I said it would do. So yeah, take that. Yeah, take that however you want. But yeah, essentially, this gets us, or with this time step, to get as much out of as much information out of this as possible. And finally, the last property of interest that I've mentioned in this code is the velocity autocorrelation function, i.e., how quickly does the particle forget how quickly does a particle forget its orientation? Here we go. So our velocity autocorrelation function tells us how quickly a particle forgets its initial velocities. At time steps really close to each other, a particle that's moving at a velocity equals 1, or its velocity in the x direction is 1. If you look at it now and you look at it really, really close to now, it's probably not going to have hit very many things, so it's still probably going to be traveling in the same direction. However, as time goes on and on and on, it'll have loads more interactions. It'll have been hit by loads of different things, and eventually all of those will have changed the forces acting on it, which will have changed the velocities. Eventually, it will forget, i.e., it will not be able to. It will not be going anywhere near the same direction. The way you calculate the velocity autocorrelation function is quite literally by taking the dot product of the velocity at some time 0 versus the velocity at some time t. And then you average that over all particles, and you average that over all atoms. This is a property that is very closely linked to the mean squared displacement, insofar as the integral of this, as opposed to the differential of the linear part of the mean squared displacement, the integral of the velocity autocorrelation function is also linked to the diffusion constant. If you zoom in closer, this isn't a particularly good one, but if you zoom in closer, you should notice usually that there is it starts at 0 and then slowly curves downwards, which we're not getting here, probably because my time step is too big to see that effect. And then if you look at the entire velocity autocorrelation function, you'll notice that very quickly by time step 20, it's just fluctuating randomly about 0. One thing quickly that I want to mention is, why was there these terrible bars? And if I click on the right window, that usually helps. There we go. Why do we have these terrible, terrible bars everywhere? The reason for this is yep. Oh, sorry, wrong one. The reason for this is, if I get the correct shell up, there we go. The reason for this is, if we look at the files that are output, remember that we said we want you to average this over, over 2,500 time steps for the velocity autocorrelation function. What it does is it outputs everything at the start when everything is 0, before finally outputting the interesting information. So actually, to get the final result that we're interested in, and to fix up that last graph that I showed you guys, the way I did that is by doing tail that, and then if you look at the new tail we've just made, that's just got the interesting information. You'll notice as well they've got this in reverse order. So the tops. Oh no, I'm telling a lie. They've got this in the right order. And if you look a bit more at the files, it will tell you. It will tell you at the top that the first thing is the index. The second thing is how much time has happened. The third bit is telling you how many things were counted here. Then it tells you a bunch of different properties, including the total velocity autocorrelation function, and then each individual in the X, Y, and Z direction if you were interested. So with that, I think that we're getting. So with that, I've talked about these advanced inputs. Here are again the same graphs that I showed you guys now with units. These are included in the slides. I've talked about the useful third-party software, and I quickly wanted to mention, if you guys are interested, there is a directory. And sorry, there is a directory. There's a directory called exercise, and in exercise, there's another input file, and the input file is exactly the same as the one we had before, except I've misspelled something. Except for instead of setting the density in the lattice region, I named a variable. And essentially, this is another LAMMPS command where I can set a variable as being something. In this case, I have set a variable called density, and density now takes the value 0.8. You can set variables to be vectors, you can set variables to be words, you can set variables to be a bunch of things. In this case, just simply I've set a variable called density equal to 0.8. And then in the lattice part of the where before it just said SC for simple cubic and then 0.6 for density, it will read whatever number I've put as the density and use that as the simple cubic density. For those of you who are interested in doing this, between now and next week, have a play around with this code, see if you're able to get it to run, see if it does everything that you need. Also, you'll notice that I've got an input script which is exactly the same as before, except it inputs Lennard-Jones.exercise instead of just in.Lennard-Jones. Please feel free to run this program, have a play around with it, and particularly, specifically, I would recommend for this exercise, have a look at how the radial distribution function that's output varies as you change the density. Like, does the radial distribution function always look the same regardless of which density you're using, or does it change? In particular, I would recommend looking at, if you're going to look at only 3 densities, I reckon if you look at those 3 densities that I've stated, so 0.05, 0.8, and 1.4, you'll get some quite interesting results. At the start of next session, I will start by going through what the results for this exercise are. So, don't worry if you're not. If you've got any questions about it, feel free to ask me. And otherwise, don't worry if you've not done it or whatever. With that, quick overview of the next session. I'll start next session by asking if there's any questions from anyone. Also, if anyone's got any questions from this session that you guys come up with, you go away and think about this for about 20 minutes and then, or even a couple of days, and then realize that something I said wasn't explained well, send me an email. Please send me an email, and I will more than happily answer it. If you could send emails at support@archer2.at.uk. I've put that in the chat. If you could send your emails to there, they will definitely, with some header about how this is for the LAMMPS tutorial, they will get to me. I will either answer them by email or use them at the start of the next session as questions. After that, I'll talk over how to compile LAMMPS on Archer, which is actually very similar to compiling LAMMPS on any other system. And I'll also talk a bit about smarter domain decomposition. So how can you be clever about making sure that you get the most out of the number of processors you're using for a job. And I'll also delve a lot deeper into the LAMMPS source code, show you some of the actual C++ code, how you can alter it to do what you're interested in, that sort of thing. Also, by next week, there will be a series of questions for the exercise class taking place 2 weeks from now. That will be made available in the GitLab repository. And, from the moment that they're up, feel free to do them whenever you want, be that before the session, during the session, after the session, whatever works best for you. I'll definitely be using that session to go over at least the ones I find most interesting, or the ones that you tell me you would like the answers to most. With that, I'd like to take one final second to really thank the people who really, really helped me with this, not least of which is Claire, who, frankly, without whom none of this would have happened. I realize now that I should also have a thanks for Juan, who did a lot of the work as well. Rui gave me a lot of inputs for a lot of the stuff that we'll see next week, but also gave me a lot of inputs on third-party softwares. And Ranga and Yang also gave me their inputs for a lot of the post-processing things. At this point, I'm happy to call it a day, and I'll stay around for the next however long people have questions for. If you have questions, please ask them. I'm more than happy to answer them.